Our second talk today is by Dr. Bruce Mellado. Dr. Mellado is a professor in the School of Physics at the University of Witwatersrand in South Africa. He has done a lot of work in machine learning and machine learning-based early warning systems. Let's pass the time to Bruce. Bruce, yours.
Can you hear me?
Yes.
Okay. I have to apologize for my doggy who likes to bark this time of the day. So I really want to thank the organizers for the invitation, and also would like to thank wholeheartedly the IDRC for the support given this past couple of years that has been instrumental in setting up the systems I will be talking about in this presentation. I've aimed for 40 minutes, leaving 5 minutes for questions in the very end. Okay, so following COVID-19 and the success of the use of artificial intelligence, machine learning for modeling and policy making and advising to policy making, our next big step and our next challenge and ambition is to create comprehensive early detection systems where we're basically, after collating as much data as possible about communicable and non-communicable diseases, including climate data, satellite data, clinical data, epidemiological, social media, believe it or not, that's very effective, pinning down a crisis, water and air quality and participatory science, in addition to the information from the WHO and the African CDC. So we want to create a comprehensive system. Now we're talking about system building, and I will repeat the word a lot, and I will try to unpack what we actually mean by that. Another very important issue, and sitting in Africa myself, is the fact that surveillance is extremely weak in the African continent. This is an example of air quality that I will be talking about the second half of my presentation as an example of the lack of coverage and how the undercovering of measurements in the continent compared to the global north. And all in all, there is an overall imbalance between our ability to collect data in the global north compared to global south. So we had to be thinking also, sitting in Africa, about certain kinds of innovations that will allow us to develop systems to collect data with which to provide sufficient information to help policymakers with early detection of pandemics or crises in general. So let's move on to the basics of how early detection works with machine learning. As we know, classical modeling has a tremendous difficulty in detecting waves. For instance, we go back to the COVID-19 example. If you wanted to answer the question, when is a wave going to take place, you couldn't possibly use classical modeling to do something like that, or any modeling for that matter. And that is the case for many crises and examples and showcases of crises you can think of. So for that, in order to go about that and circumvent the fundamental problem is to develop early detection algorithms where machine learning plays a very important role. So I'll walk you quickly through what I mean by AI in this context, because machine learning is an extremely broad set of algorithms and rules and regulations. So let me start introducing quickly the concept of recurrent neural networks. These have a particular type of neural network systems where the output layer fits into the hidden layer, and so on and so forth. It creates recurrent systems and nested systems where information goes from one layer to the other in order to create a series. It could be time series, it could be geospatial series, These kind of systems are also used, for instance, for natural language processing or any kind of sequence, okay? Now, the basic plain vanilla recurrent neural networks are well understood, but because there's problems with convergence, there's a lot of work that has gone over the years into refining them and creating modified versions of this RNN, but the basic notion is right there. Now, the type of RNNs we're interested in pertain to time series, where you basically have a system that is time dependent, whereby the output from one neural network is fed to the following neural network, and so on and so forth, as a function of time, in order to create a model that is able to create time predictions. You can move time left and right, or to the past, or do past or future. Once you have created a time series, you're able to move that to the future. In essence, how this system works, you can see here at the very bottom here, you basically create a new state, which is the result of a function, which depends on the specifics of the math or the activation functions and the inner structure of the blob A, which is a function of the previous state in time, t-1, and a bunch of features that are important to the time evolution. That's essentially, in a nutshell, what a temporal recurrent neural network is going to do. You have here a high-level representation of the unfolding in time of these recurrent systems, as I explained before. So you basically have a repetition of what I just said at the very top. I hope you can see my mouse. And at the bottom is a zoom in of the different bits and pieces, for instance, of an LSTM system, which is a modification of the RNNs with some notion of memory, where you have inside activation functions, you have flows of transfer of data and vectors, and so on and so forth. And this is basically recurrent in the sense that you have time flowing and you have vectors with time stamps that belong to a particular point in time. You will see now that in the next step, we're going to be creating geotemporal systems, where these recurrent systems not only have a temporal structure, but they also have at the same time a geospatial structure. But the idea is basically very similar, and I will define what a geotemporal recurrent system looks like a bit later in the example of how we use AI for air quality systems. So the way early detection occurs, if you're able to successfully create a model that you can convince yourself that works well, that avoids biases and all that, all the checks have to be performed through a time series, then you basically have created a model, that function here, that basically includes input features and output target features. And then you create a particular model with a particular confidence level. That's what you see here on the lower right. And what basically happens, what you're after is anomalies, deviations from those predictions. That is not to say that the model is wrong. The model has been validated. But what you basically want to see is whether the data, with all its multidimensionality, remember, we're not looking at one observable or one target. That one target is correlated with a vector X. Vector X is a large number of different dimensions of variables that are relevant to the output Y. Okay, so it's really, you're looking at anomalies in the multidimensional space. But you can, of course, always reduce that visualization to a one-dimensional one. But it's important to note that in machine learning, you are really looking at many, many dimensions, especially when we talk about deep learning. So we issue an alert, and I will show an example of how we did it for COVID-19, where you see a deviation from these predictions, okay? It's very important to note that this type of anomaly detection does not require prior knowledge of what kind of crisis you're after. You're only after a deviation from a state of equilibrium or a state of absence of crisis. That's extremely important because you cannot predict how a crisis is going to emerge. How is it going to look like? That's extremely, extremely important. And this is embedded in the map. All right, so let me just give an example of how this methodology was implemented by our team when we we still are, but now COVID-19 has waned. Detection of waves. In particular, this was a request made by the South African National Defence Force that was engaged in 2020 to help government with the problem of hospitals. And they asked the question, when are waves going to take place? And I said, look, we don't know when, but we can have an early detection system that will give you at least 2 months of time to react to a potential crisis. So basically what we did is we had all the data that was available at the time. So that was the epidemiological data. We have the data pertaining to the stringency of non-pharmaceutical interventions. Mobility played an important role. We used to heavily use Google data, Facebook data as well. So we basically put together as many data sets that were relevant to transmission and community transmission into, in this case, was an LSTM, which is a slightly sophisticated version of an RNN. It's a type of RNN. And the way it works is basically seen here. You have a time series, and the way you do it is you basically create a labeled problem. This is specified here. You have the history of the number of cases as a function of time in our province. You see the peaks and the growth, the peak and numbers going down, and you have an interim period of equilibrium, an interim period where community transmission doesn't lead to waves. And that's an extremely important data set because it gives you a data set that is consistent with lack of crisis, lack of a wave. So what we did at the time is that the LSTM algorithm that I defined earlier was trained with this multidimensional data just defined before for the interim period between the first and the second wave here, and the second and the third wave. That's what we're ready. And we actually got the worst wave around June 2021. That was the worst one. And the early detection was performed for the first time for the third, but then we used it for the fourth and the fifth. Sixth wave in South Africa has been particularly small, so it's very difficult to do modeling with such a small numbers. And then what you do is that you always have to validate the performance of your algorithm or your model. And what we did is we basically used data from the second wave to demonstrate that how the early detection was actually working. And then we created, with policymakers, you always have to reduce the amount of information to indexes, to binaries, really. So what we basically did is we created an index that was based on the output, the difference between the actual data and the predicted model based on the absence of wave. And when you see this in red, that the index is significantly higher than the threshold, and you sustain it for about a week or so, you could really know, you really knew that a wave was actually upon us. And this threshold is basically is done using frequentist techniques where we use a 95% confidence level that if the index is above in a sustained manner, the probability of a wave is at least 95%. All right, so that's basically COVID-19. And now in recent months, we'll be basically moving forward into what kind of systems can we build in order to help with the development of early detection in the long run for crisis in general. Now we know that COVID-19 is not going to be the last big crisis. Now we have to learn about how to collect data, feed those into systems, and create automated systems to predict that something bad is going to happen. We cannot predict exactly how bad it is. That depends, on a different kind of modeling, and that you can run conjectures and discuss and debate. But these systems are going to tell you that something is anomalous in the data. Something has changed. You need to get ready for crisis management. The first showcase I will be talking about is malaria, which is a very important problem in Africa. And then during the second half of my talk, I'll be talking about the system we're building for air quality, which goes of course, it affects the problem of communicable diseases, but it goes beyond in dealing with the problem of preparedness for public health crisis in general. All right, so I don't think I have to explain what malaria is in this audience. I'm certainly not a medical doctor, but in terms of public health, malaria is particularly prevalent, especially in Central Africa, but not only. In South Africa in particular, malaria is not deemed to be a serious priority. Most of the cases we get in South Africa are believed to be imported from Mozambique and Zimbabwe. That being said, we do have a certain prevalence of malaria. Now, because of the fact that most of the cases are imported, it's very difficult to model malaria using South African data. So we decided, as we will see in a minute, to concentrate on Kenya, which has a much higher prevalence of malaria. Now, that being said, it's important to note that malaria still remains a very serious disease. Africa takes up about 95% of the total case, about 96% of all the deaths. So this is clearly a very, very serious problem, and a classical example that can be used for early detection systems of the type that we want to put together. And we've done some feasibility study, but now starting to write a paper about the use of this type of deep learning and predictive deep learning with the Kenyan data. Now, the use of satellite data has been already discussed in the literature. This is a very good paper that came out about 2-3 years ago. The European Space Agency is providing a lot of data that is, for the most part, untapped. But the functionality of that data, the type of data, how that data can be used is understood. Because this data gives us information about the mosquito habitat, about humidity, about vegetation, land-related issues, et cetera. So the satellite data is actually very good. We don't need high resolution. The drawback of satellite data in general is that it doesn't provide high resolution. But for this type of exercises, we don't need to go that deep in the geospatial picture. So satellite data is actually a major resource and a very important input data set to early detection systems, especially when it comes to malaria. I will make a comment on how important that is for air quality. The importance of satellite data for air quality is not as much as important as in situ on the ground measurements. But when it comes to malaria, certainly satellite data is very important. We've been working with satellite data from the European Space Agency. We're now adding a lot of the products that NASA is providing. In fact, I came from a workshop organized and funded by the Carnegie Foundation, where a lot of these products were showcased to us. But the fact of the matter is that this European Space Agency provides a tremendous and amazing data set, massive amounts of data that is highly accurate, that has been processed, that is very well documented, as you will see in a minute, and that provides a very good insight into the macroscopic picture of the habitat of the mosquito that can be used for predictions. So the showcase here, as I already indicated, that we picked was Kenya, in that we had historical data for the 4 provinces that are contiguous to each other. And because of the geography, you start basically developing the corresponding geospatial picture and tools for the specifics of Kenya. And as I said earlier, we dropped the idea of doing it in South Africa because we just don't have enough cases to actually create models. Malaria is not a priority in South Africa. It's more HIV and tuberculosis that are more prevalent in South Africa. So the satellite data here now, you really have to dig into the documentation. You really have to talk to experts, and you basically end up having quite a collection of data, quite a multidimensional system of up to 50 different variables, which is basically different combinations of the emission and reflection of electromagnetic waves on the surface. And depending on how the reflection occurs, the polarization, and all that stuff, you basically are able to infer a number of indexes. Each index has a notation, and each index has a particular relevance to the mosquito habitat. And as such, how the malaria will actually propagate. You have here an example of data, historical data, corresponding to the period of the data that we saw in the literature from January 09 to December 12. You can see there the different indexes and the smoothness of the data. So you really see a continuous generation of data and archiving of the data by the European Space Agency that you can retrieve and go back in history in order to be able to make future predictions. So as you know, this is the whole notion of early detection, is to really have historical data, to really have time series in order to train your algorithms. And there is plenty of data to go by when it comes to the satellite systems. Then you use custom-made LSTM. We also have built a graph neural network. I don't have time. I have a lot of material to cover today. But basically, these things are well understood. You run hyperparameter optimizations. You divide your data set into testing and training and testing, and then the results are here. The results are here. You can see on the left-hand side some data from one of the provinces, Riverine, which we're now documenting in a new paper. More or less, the agreement is actually okay. It's very difficult to get perfect agreement, of course, but this really gives you, within tens of percent, a prediction. You can see the actual cases and the predicted cases that are actually following each other fairly well. And this is basically in modeling fairly good, in that classical modeling, we have a great difficulty in dealing with the nonlinear character of the changes. There's a strong modulations that need to be embedded into the modeling, and this qualifies in general as good agreement, and we are documenting it as we speak. And this is, by the way, prediction. The red is a prediction. This is not the training data, it's the testing data. All right, so our ambition, before I move on to the air quality, is to create maps of for early detection, prediction of hotspots, with certain probability for hotspots to emerge and for the entire continent, using, for the most part, the satellite data that I just described. So it's really a problem of systems engineering, where you collect a lot of data and you continuously process it as the data from NASA and the European Space Agency is being produced. I may add that I found out last week that there's a project supported by, I don't know whether it was NASA or someone else in the United States, where now they are doing the same thing, but for air quality using satellite data. So these notions are already gaining momentum, the notion of gathering data and creating maps of risk and hotspots, where policymakers at the national level, but also the continental level, can really look into the corresponding risks. Okay, so I'm going to move on to the second half of the presentation about air quality monitoring, which is something we're very excited about, because this is, as you saw earlier, one of the biggest data gaps that we have in Africa, I think in the world in general, even in the global north, but especially is particularly acute in the global south. And air quality is responsible, paradoxically, for more deaths in Africa than, for instance, HIV or tuberculosis. And it's not just the fact that, millions of people die, of poor quality, and it's getting worse and worse and worse, is the fact that air quality is a proxy to vulnerability, and it allows us to establish vulnerability towards crisis. So this is strongly intertwined with the notion of early detection systems. And air quality just happens to be really ubiquitously absent, as you saw in the map. And this is one of the biggest problems that we have in Africa today, is the increased concentration of pollutants, but in particular particulate matter and other nasty substances, and the fact that it's getting worse and worse as urban population gets bigger and bigger and bigger. So this, I think there's a lot of traction for this globally, and we basically decided to put together all our knowledge in system building to create a prototype, and you will see this in a minute. We created a consortium that the ACADIC is a member of, and again, I want to really thank the IDRC and other stakeholders. We had to bring the European laboratory CERN, who is one of the major stakeholders supporting, with in-kind contribution for the technical staff. We also have to acknowledge the partnership with industry such as Nordic Semiconductor, Perovskaya Solar, and Health Matrix, which provide invaluable support, technical support of their technologies, because in order to build complex systems, you cannot do everything from scratch. There are things you just simply cannot do. And we basically develop partnerships with industries that are sensitive to the problem of cost effectiveness, that provide state-of-the-art technologies. In particular, as I will say in a minute, the problem of communications, Internet of Things, cost-effective solar cells, and the problem of breathalyzers. So I will, just give you a very, nice example of how important it is to work with industry. Health Matrix is a Boston-based company. I will give other examples as well here. So what Health Matrix vision is that you can breathe into this a breathalyzer, and with a very basic measurement of what comes out of it, you can actually detect many things. You can even detect pandemics. You can detect crisis in the system. You can detect individual-based problems, but also community-based problems. So this is a very important type of data that is easy and cheap to produce, that generates sufficient data sets to generate these early detection systems. And of course, the communication with the cloud and artificial intelligence is an absolute must. We'll skip this here. So let me go into our proposal for to deal with the problem of air quality monitoring globally, but in particular in Africa. As you saw in the map, we almost have no measurements on the ground. And even though satellite measurements are great, their resolution goes into 5 by 5 kilometers, 3 by 5 if you're lucky. That's not enough to establish hotspots. Hotspots of poor air quality, for that you need basically on the ground measurements, because you need a much better resolution of a few hundred meters, not few kilometers at a time. And also so satellite measurements are a very important complement, but when it comes to air quality, it's not enough. And what we are basically, the system we're building here is the merger and the marriage between artificial intelligence, Internet of Things, and sensors. Those are the three basic components, and we have established partnerships with industry to deal with the issue of sensors and communications, where we provide artificial intelligence. So let me split the problem into two: the IoT development, the Internet of Things, which the field agrees is the way to go in order to be able to measure the quality of air in a sensible way in the global south because of cost effectiveness, and that is Internet of Things. We have wireless communications. So clearly, developing systems is actually complex. This is a graph of the structure of the project by one of our project managers. You can clearly see that it is complex. So it's evident that healthcare specialists, public health specialists have to work with people like us that bring the systems engineering to the table to build comprehensive systems such like this. Okay, and this is not a very, very complicated system, but it's already complex enough that interdisciplinary collaboration is imperative. So we've basically built a topology of Internet of Things based on state-of-the-art communication technologies that are cost effective. This is actually not as trivial as it sounds, because you have a lot of proprietary stuff around, and there isn't really the business models here. They don't really are after cost effectiveness. So I believe this is one of the unique efforts that we have around the world to build complete systems on the basis of cost effectiveness without compromising performance or quality of the measurement. And that is a fairly complex and multidimensional optimization. So the result of one of the first optimizations, the graph you see here, of the structure of the system, where you have master nodes, slave nodes, different types of communications, 4G, radio frequency communications, and so on and so forth. I'm not going to get into the details here, and a bunch of technologies that we have chosen to be optimal in the markets in terms of cost-effective performance. You see here examples of setups of one of the sensor technologies. I'm not going to spend too much time here. This is not an engineering audience. You have another setup here to look at another type of technology, Sensorion technology. This is after months of work. This is a technology we are essentially going to be using for the measurement of particulate matter. This is a Swiss technology and this is a Swiss company in Zurich that, believe it or not, Switzerland is able to generate cost-effective systems. And this is probably the best in the market today in terms of measuring the density of particulate matter in air through laser and optical surveys. And this is a system basically put together by us. Then you basically have that. On the left is a Sensorion sensor with the state-of-the-art of cost-effective technologies for communication. You need to have a controller and then a communication that generates the corresponding signals for the signals to be propagated through networks. Okay, and that is what Internet of Things is all about. And we signed an agreement with Nordic Semiconductor. They're able to provide chips for just a few dollars a piece, and most importantly, they give quite a lot of resource to us in terms of their technical team, which is an extremely valuable piece of information. Then you basically build systems. This is an example of the type of components you need to put together. Everything has been checked. I will show some measurements now. And of course, cost is extremely important. You have to really create a cost-effective system that doesn't compromise in performance for IoT. And you have here outputs from our engineers. That's for the master node. And these lists are for the slave nodes, which are supposed to be cheaper. There has to be more of them, of course, surrounding the master nodes. And the master nodes surround the existing stations that we have already in place, of course. The idea is not to replace the existing system, but to enhance the system with a lot more measurements that will allow us to have granular information on the ground at acceptable cost to African governments. Then a very, very important aspect of the development is power consumption. That's really the Achilles heel of any system, is how much power is consumed. And then you have to work very closely with the manufacturer to really get to the nitty-gritty of the different modes of operation of the devices. So you need to develop that expertise. You really want to be serious about developing IoT systems that don't require cables, and this is extremely important for Africa. If you start talking about expensive setups and cables, then basically the whole thing goes mute. You really need to have affordable systems that are plug and play. Yeah, put it there. Even if they're stolen, you replace them. That's far cheaper than using existing commercial off-the-shelf systems that require a massive amount of investment. So power consumption becomes core, and we have recent results from our engineering team that made a number of measurements. You can see here the measurement of particulate matter. it's extremely important for the design to basically measure consumption and currents as a function of time, and understand where and how, without compromising the quality of the measurement of particulate matter, we could reduce the consumption to ensure that we could live with batteries or solar cells. This is an example of the power consumption of the Sensorion sensor, of measurements like CO and VOC and temperature and humidity, which is significantly less. And then the other very important piece in the puzzle is basically how much power do we have to spend to transmit the data from one sensor to the other. So that's essential as well. And the good news is that that's not a major part of the consumption budget, where and that has to do with the fact that, yes, there's a lot of consumption. 90 milliamps is very big, but it basically happens over the span of less than 0.1 second. So the idea is to basically make an optimization that allows us to wake up the devices, measure, send data, and turn them off, and do the shipment of the data immediately after the data has been collected, without having to deal with memories and things like that. Now, let me move on to the AI part. So this is the IoT part, the hardware part. Now we have to embed that into AI systems. And I was driving the conversation towards this. So remember that I started the talk talking about recurrent neural networks, temporal systems. Now you're basically adding, in addition to time, you're adding geospatial location, 2D or 3D. But this is typically 2D. So you have basically the same recurrent system, but instead of just having one variable to unfold, time, you basically have a geospatial picture in addition. So what happens is that you have, you take a snapshot in time, and within that time stamp, you have a corresponding geospatial interconnection between the nodes, and then the whole thing is moved dynamically as a function of time. This is basically how you would define geotemporal systems with graph networks or sophisticated LSTMs or something like that. So the issue of particulate matter is fairly complex, because if you think about all the factors that contribute to its concentration, you start having quite a multidimensional system. So it's not just a PM2.5, but basically everything that surrounds it, that would basically that would talk to the diffusion of particulate matter in space, and the geospatial picture and temporal picture, and the different factors that contribute to it. Now, those, through research of individual factors, that's already understood, but now our job as system engineers and data scientists to bring everything together into a comprehensive system that now gives massive useful information to policymakers, okay? Because all the research has really been done for the basics of how PM2.5 and particulate matter basically evolves. And the important thing now is to have data for large swaths of territory with which we can issue alerts. I think I'm going to run faster here. This is too technical. And there are basically interconnections between the nodes that includes the direction of the air and the corresponding angles. Then you develop a particular type of recurrent systems. In this case, we use graph neural networks, which are particularly attractive in that they're highly configurable systems that you can turn them into recurrent systems through a geotemporal picture where you have different types of inputs. There are inputs that interconnect nodes, and there are inputs that are intrinsic to the node, and you separate them in the training. And then, of course, you put satellite data on top of that, et cetera, et cetera. So it becomes fairly fancy. You have examples here of data, how data is collected by the stations. And we don't have time to show it, but we're basically showcasing how this is correlated with satellite data. And then you develop models. This is a showcase. We have a collaboration with the agency in Switzerland that measures air quality. Their quality of air measurements are very good. And we use those as baseline. You can see overall that the model, the ground truth, as we call it, and the different models that we've developed agree more or less okay with the graph system. The GNNs perform better than the others. That's sort of expected, but it's really nice to see. And it's really nice to see how the model is able to follow very closely the actual concentration of particulate matter. This is results of the modeling for South African data, because we work with the local agency in South Africa, SAA-QIS, which is funded by the South African government. All right, and last, I think I'm finishing in time to leave 5 minutes for questions. We now wrap everything into one system, and I'm repeating the word system for a reason. We develop systems. We don't develop, so to say, test stations or devices for individuals to make some measurement. We're talking about systems that are self-contained, that are useful to governments and policymakers because they collect a lot of data to provide alerts. Okay, we have just recently signed an agreement with CERN, the European lab. They have this program called the CERN Green Village, and they have agreed to host this prototype in an area that, believe it or not, is highly polluted. So it's not as polluted as, for instance, an African city, but it's certainly one of the most polluted sites in Central Europe. And I will show that in a minute. And we are actually collaborating with them. And also we are very grateful to them because they are providing quite a lot of support in kind in terms of their engineering. As a matter of fact, some of the pictures I showed earlier were taken at CERN. Because we have a collaboration with them, and we're developing some of the hardware in Geneva with them. And the idea, and this is, I think, my last slide, is you can see here the Google map of CERN. CERN is this triangle here. I hope you can see my mouse. Because it lies in the border between France and Switzerland, there's very few entry points into each country. And there is a very, very high concentration of cars going into France or into Switzerland, or at the same time. You have very high levels of PM2.5 here. So CERN has agreed that we deploy the entire system this year and the next to demonstrate feasibility of the hardware, the communications, and the artificial intelligence, providing support at all levels. And that, of course, also includes support from our funding agency. And with this, I finish. Thank you very much.
Thank you very much, Bruce. Do we have questions from the audience? Yes. 1 sec, please.
Thank you very much for the presentation, and it's good to know this kind of the world of these AI-based detection systems. I just have some questions in terms of the outcome of the AI. I mean, in the past, we have, for example, in the early detection, the systems, there is a lot of traditional detection approach has been used already. So I'm just curious about, the AI-based approach, how much of, in terms, for example, to improve the early detection, the warning signs, by compare with the traditional approach, many of time series, we have been implement many of those kind of the traditional approach in the past. So how AI-based approach are actually can improve those kind of early detections, and how this kind of AI could help even in this kind of air qualities could kind of improve those kind of the air quality modelings by compare traditional approach that other people have been adopted. Thank you.
Okay. All right. That's a very good question. So this has to be done on a case-by-case basis. So let's talk about air quality. There's already quite a number of papers in the literature, mostly in China and the US, on the advantages of machine learning over classical approaches. Now, one of the fundamental reasons why AI is more effective is when you deal with large dimensionalities of data sets, okay? So you're not talking about describing a one-dimensional distribution. You're talking about describing a one-dimensional distribution that is correlated with 50 other variables at the same time. The ability to predict heavily relies on picking up these correlations. There's just no better tool in advanced analytics than machine learning to pick up these correlations in large dimensionalities. Now, ideally, we would like to be very sophisticated in our modeling and be able to describe through classical modeling 50 dimensions. That is fantastic. But when push comes to shove and you deal with crisis, many papers have already demonstrated that when you deal with large dimensionality, systems like graph neural networks and recurrent systems are really the way to go. So the literature, I wouldn't say is vast, but certainly is well established when it comes to air quality. Same thing, for instance, now in a lot of the early detection that has been developed for public health is mostly for diagnosis. You have a vast body of work, for instance, for cancer and similar diseases, where again people have resorted to using machine learning because they were able to do just much better. Because developing classical models, it takes a long time. It's very complicated, and the moment you have 50 or 100 variables, then you really have a very serious practical issue. So the body of work is there. I mean, it's not something we are not saying that we have done a breakthrough ourselves in demonstrating that AI is better. What we are doing is developing systems based on those breakthroughs and those and those papers and that literature that indicates that machine learning simply overperforms in practice when modeling is available, if available, which is probably most of the time is not available.
Okay, thank you very much. There's another question in the chat window, but I think it's already answered. The question is whether the satellite data is openly available or is it closed data? I think your Dr. Ali Asghari, I think is your colleague, has already answered that.
Yeah, I have a follow-up
to
question to that though.
Yeah.
I have a question. So for machine learning, like what are the challenges for as like something that humans can do, but that machine learning cannot mitigate in terms of bias and these kind of aspects?
Yeah, so I mean, the issue of bias detection is very well understood in machine learning. How to ensure that the algorithm, the model that has been created is not biased by whatever reason. So there's many ways of doing checks and balances for that kind of stuff. And of course, always, as in any model, and here machine learning is not any different from any model building, you need to have a thorough evaluation of performance, and you need to have the data sets available to validate methods. I mean, this is always the case. You cannot just, and this is probably one of the biggest problems with advanced analytics or any new technology, you really have to use it properly. And unfortunately, when it comes to machine learning, there are people that don't use it properly because they are not yet trained to understand how to open the box of what machine learning is. So you really have to have a lot of experience, a lot of intuition, and a lot of sophisticated tools that exist today in order to assess biases that can be generated one way or the other. But that's not a fundamental problem. It's just that, unfortunately, using machine learning requires many, many years of experience. And it's clear that the public health specialists have to work with data scientists in order to develop these systems. These are very complicated systems that cannot be have to be developed on the basis of very particular type of expertise.
Thank you very much. Let's thank our speaker again.